We are in ring theory. So basically, a ring is a structure where one set and two operations are given, R along with addition and multiplication is said to be a group. If R plus is an abelian group, means addition must be binary, associative, there must be identity for addition, and every element in R must have inverse with respect to addition. Moreover, to have abelian group, addition must be commutative. So these are the 5 conditions addition must satisfy on R. At the same time, multiplication is the multiplication of members of R. Multiplication must be binary and associative, and at the same time multiplication should distribute over addition from left as well as from right. These are the requirements of ring. So we memorized the definition of ring. Now see here, we want to define homomorphism on rings. So suppose we have R and R dash as 2 rings with us. So naturally R will have its own addition and multiplication. At the same time, R dash will have its own addition and multiplication. And we are defining a map from R to R dash. When to say that this map is a homomorphism? If this phi satisfies, preserves both the operations. If I take phi of A plus B, we must have phi of A plus phi of B. So image of addition must be addition of the images. And second condition is phi of A into B must be equal to phi of A into phi of B. So phi must preserve multiplication. This is the basic requirement. If both the operations are preserved under this map, then this map is called as a homomorphism. So let us deal with this example. We have F to be a ring of all functions mapping R into R. So we have the set capital F, which contains all functions. What kind of functions it contains? Whose domain is R and codomain is R. So real valued functions of real variables we are dealing with. Now, how do we define? How do we define addition on the set F? So let us see. If at all I take 2 members from this set, I want to define F plus G. So these being functions, I have to operate them somewhere. I'll operate them on some X. Then F plus G of X must be equal to F of X plus G of X. This is our usual definition. F of X plus G of X. So this way we define addition on the set F. And I want to define multiplication of the functions. So how do we define multiplication of the functions? F into G. I want to operate this on X. So how to operate this on X? This is just the product of the functional values. So F of X multiplied by G of X. And this is true for all X belonging to R because the domain of this function is R, the whole real line. We know that addition forms a kind of group because addition is binary, associative. 0 will be 0 function. 0 function is whose output is always 0. So 0 function will play the role of additive identity, and Talking about the inverse, we know that f plus minus f. So negation of the functional value will be the additive inverse. So we know better that f plus forms an abelian group, and this kind of definition of multiplication of functions we know is binary as well as it is associative, and we know the output is the product of real numbers, so it is distributive even from left side as well as from right side. Now we would like to go back to a mapping. Let us define a map phi a from f to r. We are handling two rings. F is the ring of functions and R is usual ring of real numbers. We will define evaluation homomorphism. How to define it? So phi of A, when operated on F, it gives you F of A. So let us see. We have two rings with us. I would like to just go by another color. Okay. See here, I have the set of functions as my domain and the ring of real numbers as the codomain, and let us define our function phi. From this F to R. How will we define this? So for a fixed real number A, what it will do? Phi of A when operated on F, it will produce F of A. It will produce F of A. So this kind of operation, will it preserve both the operations, that of addition and multiplication? Let us see one by one. So let us have phi A operating on the sum F plus G. So very naturally, what will be the output of this? Output will be F plus G operated on A. F plus G operated on A. This will be our output. But by the given definition of addition, you can see what is going to happen. This will be F of A plus G of A. So this is equal to F of A plus G of A. Now can I call F of A as phi A of F? So very naturally this is going to be phi A of F, and plus this will be phi A of G. So what we have shown, this phi A preserves addition. You can see under phi A, the image of F plus G happens to be the sum of the images. So very naturally phi A is preserving addition. Now let us go to multiplication. Let us have phi A operating on F into G. So what happens? This is nothing but F into G operated on A. This is not a composite map. We are not dealing with composition. What we have as our definition is F into G when operated on X, it is just the product of the functional values. So the same way, what we'll get is equal to F of A into G of A. And I can read F of A as what? Phi A of F. So I can read this as phi A of F and multiplied by phi A of G. So we can see the multiplication is also preserved under phi A. So whatever map just now we defined by phi A, this map is known as evaluation homomorphism. So it's a homomorphism, as you can see. So if you want, you can have this Okay. So as a question, you can write down, show that phi A from capital F to capital R is a homomorphism, ring homomorphism. So what you need to do is you need to show that addition gets preserved under this particular and scalar multiplication is also preserved under this. So hope you have taken the screenshot of this particular. Ready for the next?
Oh, madam.
Yes, ma'am.
Okay. Now I move ahead. So you can see this was evaluation homomorphism. So this is one of the best examples. The second example we have seen already. Wait a minute. Wait a minute. Okay. The second example we have already seen is that of phi from Z to Zn. So we dealt with the rings Z and Zn. Z are usual set of integers along with usual addition and scalar, usual multiplication. So it forms a ring. Then you have Zn. Zn means all residues when divided by n, along with plus modulo n and multiplication modulo n. These two are our usual rings under process. And let us define our phi as what? Phi from this ring to Zn. So if I operate this phi on any A, what I should get is A modulo n, means remainder when A is divided by n, A modulo n. So this is what is the output. So very naturally this phi is a ring homomorphism. Phi preserves addition, phi preserves scalar multiplication. So if you select any x and y and add them, the output is going to be x plus y divided by n. Whatever remainder you get, that is your output. And this further can be read as what? X bar plus y bar. Let us put bar overhead just to denote the remainder when divided by the number. So what you can say, x bar is nothing but, you can say x bar means when x divided by n, whatever remainder is there. So it itself means it is phi of x. I hope you agree. And talking of y bar also can be referred to as the remainder when divided by n. So this is phi of y. So phi preserves addition as you are watching. Now let us move to multiplication of the numbers. So if I have two integers with me, x and y, and I have their product, then phi when operated on product xy, it will produce xy bar. Can I say so? I think we are quite familiar with this notation. When I put bar overhead, it means the remainder when divided by n. So I'm dividing this product xy by n, and whatever remainder I get, the remainder will vary from 0, 1, 2 up to n minus 1. So this is what we have. And we know better that product xy bar is itself equal to x bar into y bar. And x bar is nothing but what? Phi of x multiplied by y bar means phi of y. So what we can say is phi preserves the multiplication also. So this particular is the best example of ring homomorphism. This is a ring homomorphism. So you can take down this as show that phi from Z to Zn defined by phi of A equal to remainder when A is divided by N is a ring homomorphism. And you can show that phi preserves addition and phi preserves multiplication also. So I hope you can take screenshot of this. You can formulate your own question out of this and write down the answer. Is this fine?
Oh, madam.
Okay. Can I move ahead?
Oh, madam. Oh, madam.
Okay. Now I move to the thing that we discussed few hours back, structurally identical. What I mean by structurally identical is nothing but isomorphism. Okay. So let us deal with the definition that we have already seen. The definition of isomorphism. If we are having two rings R and R dash, and a map phi from R to R dash is a homomorphism, and moreover it is bijective function, then we call it as isomorphism. So homomorphism, which is 1, 1 and on 2, it is called as isomorphism. The map is called as isomorphism. And the structures R and R dash, they are said to be isomorphic structures. R and R dash are isomorphic structures. Now, one of the best examples is we have Z and 2Z. This example also we have already discussed, but let us revise it. Z and 2Z. What I mean by 2Z is every integer is doubled, means the set of even integers. Z along with usual addition and usual multiplication is a ring, as we know. 2Z with usual addition, because sum of even numbers is again even, and multiplication of even numbers is again even. So these two actually satisfy all the axioms for ring. So Z plus dot is itself a ring, 2Z plus dot is itself a ring. I have to define a function from these structures from Z to 2Z. So we can double that integer. Very natural trend is, if I take any x, then its output will be twice of x. So this is a very natural function out of this. Now, will this phi preserve addition? Will the phi preserve addition? Let us check it. I hope you can answer. Phi of I have x plus y. What will be the output? Twice of x plus y. And to be more simpler, I can call it as what? 2x plus 2y. Now, can I read this 2x as image of x? Yes, I can. I can call 2x as phi of x. And image of y as phi of y. So what I observe out of this is phi of x plus y is phi of x plus phi of y, meaning phi preserves addition. Phi is preserving addition. Now, does this phi preserve multiplication? I have phi of x into y. I know whatever I input is getting doubled. So output is going to be twice xy. Now, I know that phi of x into phi of y, because I want this to be the right side. So very separately I am solving this. Phi of x into phi of y gives me twice x multiplied by twice y. The output is 4 times xy. So 4 times xy cannot match with twice of xy because xy is the same. Twice of it is equal to 4 times. It will happen only in the case of 0. Otherwise, it is not possible. And we want this to be true for every x and y, every pair. So this is not possible. I feel all of you have got. So very directly what I can say, phi of xy not equal to phi of x into phi of y. So in general, this is not true. So phi does not satisfy homomorphism property because homomorphism needs to preserve both the operations, addition also and multiplication also. Addition is satisfied, but multiplication is not satisfied. So it's not possible. And that is why what I can say, phi is not a homomorphism. Now whether phi is an isomorphism or not, so I have to check for 1-1 ontoness. Actually, it is not itself homomorphism, so it cannot be isomorphism. I mean z plus dot will not be isomorphic to 2z plus dot. But let us focus to the fact that this definition of phi is not onto, because if I take phi of x is equal to 5 or any odd, will mean that it is twice x, and this will imply that x is 5 by 2. But x equal to 5 by 2 is not an integer, it doesn't belong to z. And that is why phi is not onto. Do you agree that phi is not onto?
Yes, ma'am.
Sure. Your codomain is twice z. How do you get odd integer over here? How would you get odd integer in 2z?
नाही भेटणार मॅडम.
So this explanation is quite wrong, isn't it?
Yes.
So whatever number you have in your codomain will be twice of something. I feel you are getting me. I misguided. Okay. So whatever number you have in 2z is already twice of something. So it will be like this, twice 5 by 2. 2 is getting cancelled. And whatever result you are getting, that is a member of z. That is a member of z. Got the correction?
हो मॅडम.
So phi is?
नाहीच मॅडम, होमोमॉर्फिझम कुठे?
Phi is onto.
हा, ऑनटू आहे.
Yes, phi is onto, but it is not homomorphism, so it cannot be isomorphism. Got the point?
Means 1-1 नाहीये onto आहे.
1-1 पण आहे, onto पण आहे, पण homomorphism.
onto म्हणल्यावर आपण x equal to y घेतो ना समज.
एक second. Yes, I'll help you. See here. What was your domain and what is your codomain? Domain is Z. Codomain is the set of even integers. Do you agree?
हो मॅडम.
And how is your function? Whatever you input gets doubled over there. I hope you are getting my point. Your input is from the domain. So input will be from the domain and output goes to the codomain. So output is always an even integer. Your codomain is the set of even integers. So whatever number you choose out of this codomain will be itself even. Followed my point?
मॅडम
हा.
नाही समजलं. आपण ते म्हणजे एकच पॉइंट घेतो ना आपण 2x थोडी घेतो ते फंक्शन झालं ना मग.
Set, okay, let us have our domain. Okay, I would like to go with Venn diagram. Just for explanation, I would like to go with Venn diagram. Okay. See, this is your domain. This is your codomain. Okay. You'll just tell me what are the members of your domain. 0, is it there?
Yes.
1,
Integer.
-1
2,
2.
3,
3
and so on. Okay. Talking of
Minus.
negative side, -1, -2, -3. I say and so on. Okay. Now I would like to go for this part. What are the members of 2Z? Is 0 a member? Yes, 0 is there.
4 6
Yes, 2, 4, 6, and so
8
on. Okay. What are the next members?
-2
-2, -4, -6, and so on. Is it right? Now, you just tell me, is every member of this 2Z mapped somewhere?
Yes.
Every member of 2Z has a pre-image. I hope every one of you agrees with me. If not, you tell me a member which is not having any pre-image. Pre-image of 2S. I'm extremely sorry.
8 पाहिजे ना मॅडम.
What has happened? Huh?
अच्छा 1 ची 2.
Pre-image of 2 is 1. Pre-image of 4 will be 2. Okay. Pre-image of 6 is 3. Pre-image of -2 is -1. That of -4 is -2. That of -6 is -3. And that of 0 is
0.
0. So just tell me a member of 2Z which is not having pre-image. Do you have?
No.
No, there is no number which is not having pre-image. Every member is having a pre-image, and that is where the function is onto. Okay. And I have to say our function is 1, 1. Talking about 1, 1-ness. Yes, can you help me? 1, 1-ness. I say, suppose phi of something. Suppose phi of A is phi of B. Images are same. We want to check for the pre-images. What is phi of A actually by your definition? It is double A, and to the right side it is double of B. I hope you agree. What will happen next?
2 times A equals to B.
Yes, I got A equal to B. So whenever images are equal, we find pre-images are also equal, means phi is 1, 1. We got phi to be 1, 1, phi to be onto. But phi could not satisfy our homomorphism property. That was the thing. Okay. So here we have mistaken. I hope. So that is what I wanted to correct. And here, yes.
But for isomorphism, it has to satisfy these three conditions, na one, onto, and homomorphism.
Yeah,
So
it is not.
homomorphism.
Yes, homomorphism property is not satisfied. Surely it is not an isomorphism. See what I mean to say? It is not an isomorphism, but it is one as well as on two. Okay, I mistook this as a 5 odd, and that I just wanted to correct. Is this clear? Mainly to Gauri. Is it clear? Are you there? Okay, others, have you got it?
Yes, ma'am.
Okay, okay. So I think this is okay. We just dealt with the definitions of homomorphism and isomorphism today, and we just tried to have some examples based on it. Now let us move to a further concept, that of a zero ring, and then we'll stop. What I mean by zero ring, if suppose I have singleton 0, set singleton 0, naturally addition works over there. 0 plus 0 is 0 back. 0 into 0 is again 0. So all my needs are satisfied with 0. So singleton 0 itself satisfies all the axioms required for a ring, and therefore we call it as zero ring. I hope you are getting me. Zero ring is singleton 0 with addition and multiplication. Further, 0 acts as multiplicative identity element as well as additive identity element, because I'm getting the same number back over there. So see the concept of identity element. Usually whenever we multiply by 1 to any number, the number is back. But 0 is a special. You have singleton 0. Your set contains only 1 0. And what you observe, if I multiply 0 by 0, I'm getting 0 back. And there is no other entry. If there would have been any other entry, like suppose 5, 0 into 5 will be 0, which is not returning back 5 to me. So that kind of thing is not there because my set contains singleton 0. So 0 plays the role of multiplicative identity element also. I hope I underline this. In this case, 0 is acting as multiplicative identity element. Have you got the concept of multiplicative identity? What I mean by multiplicative identity, suppose I have number A with me, I multiply by my identity element E, and I'm getting back A, then that this E is referred to as multiplicative identity. So in this case, you have 0 into 0 back a 0, means 0 will be multiplicative identity. Only in this case, nowhere else. Is it okay? So a number multiplied by a 0 is the number itself. So 0 is the multiplicative identity. Got me?
Yes, ma'am.
Okay. So for today, I would like to stop with this concept. I suppose you have got what is meant by a zero ring. Is there any question?
No, ma'am.
मॅडम
हा.
आता ते हायलाइट केलेले ते पण लिहून काढायचंय का?
हा, घेतलं तरी चालेल, एक स्क्रीनशॉट घेऊन टाका. Okay, so today I won't ask you to continue. Okay.
Okay, ma'am.
All right.
Thank you.
Okay. Okay. Bye.